So I think Dimitris will conduct the.
Okay, so welcome to the second week of this meeting, and we start right away with Cedric Bernardin from University of Nice. So please.
Okay, so first I would like to thank Abhishek for taking care of the organization of the conference. So in this talk, I will discuss some problem of large deviation functional in two-dimensional strongly asymmetric systems. So the real novelty of his work is really that it is in two dimensions. So right in one dimension, it is quite a lot of the things that I will present are known in one dimension. So this is a joint work with Julien Barré and Raphaël Chetrit from Nice. So during the last years, there has been a lot of interest in the study of large deviation functional of interacting particle system, and in particular since the introduction of the macroscopic fluctuation theory. And in particular, people were interested in the behavior of large deviation functions for density, current, the scalings of the currents for a closed system or for open systems. So in particular, I would like to mention this work of Bodino Derrida, and also all this macroscopic fluctuation theory introduced by what is called the Italian team, even if it is not only composed of Italian people. Okay. But recently there has been some interest in higher dimensions, how so people were interested to look at this question addressed here in the case where you are, for example, in two dimensions. So in this talk, I will focus on a system in two dimensions. So first, I would like to speak about weakly asymmetric driven diffusive systems. So I will explain what I mean by weakly asymmetric, and later I will move to strongly asymmetric systems. So what I will present will be focused on some macroscopic equation, even if, in fact, I am interested in the behavior of microscopic system, but I will start directly from the macroscopic description of the system. So typically, we are interested in some driven diffusive system, so closed system without boundaries. So for example, here it is only, the system is considered on the torus, okay, in two dimensions. And then we assume that the system is described by some conservation law in the form, for example, for one conserved quantities that I call the density, but you can imagine that it is the energy or something else, what you want. There is only one anyway. And so the macroscopic behavior of the system, the typical behavior of the system is described by this conservation law with a current which takes the form of some diffusive term and some drift which is regulated by some parameter nu. Okay, so here I will call rho the density, but it can be something else. Okay, J is just the density current. Here D is the diffusion matrix. So here I am in two dimensions. So here is the gradient is a two-dimensional vector. This is a matrix, and F is also a two-dimensional vector. Okay, and so the parameter which is here is quite important. It regulates the strength of the drift. The drift is conservative since we have a divergence here, but there is a drift. So the typical example of microscopic system for which you can describe by this macroscopic equation are, for example, weakly asymmetric lattice gas. So here you have a picture in two dimensions where you have a grid with some particles. On each side you have one particle or zero particle, and each particle tries to move, like for example some random walks. You can imagine that there is also some more interaction. You can jump from with some finite range jump probability, and we assume that there is some exclusion rule, so the particle cannot jump on the site which is soon occupied by some other particle. Okay, so typical example of systems that I am interested in. And in fact, the first motivation of his work came from the field of active particles. and but I won't discuss that here. Okay, so if you want to imagine what is the microscopic system that I'm interested in, you can think of this weakly asymmetric lattice gas. Okay, so the equation that I wrote before was just to describe the macroscopic behavior of the system, but if you want to be more precise, you have to introduce the fluctuations around this typical behavior, which formally can be described by this now equation, stochastic differential equation, where you have some white noise, which is regulated by some symmetric matrix, some mobility, okay? And okay, this is just the standard form of the fluctuating hydrodynamics around the typical behavior. And this, so what describes this stochastic partial differential equation, and it will explain why I call this system weakly asymmetric. It describes the behavior of the empirical density, okay, rho epsilon, when you consider some system, very large system with size epsilon minus 1, so it is very large, and you look when you have a drift term which is of order epsilon nu. So with respect to the inverse of the system size, it is very small. It is the reason for which I call it weakly asymmetric. And then you have to look at the system. The correct time scale to look at the system is a diffusive time scale. So epsilon minus 1 is the inverse of the system size. And the SPD that I wrote before describe, in fact, this empirical density in this time scale. Okay, so here x is just in the torus, the two-dimensional torus, t is the time, and you have this approximation of the empirical density in this time-space scale. Now, in fact, we can also say more. We can say that we can give some formula for the large deviation function for the empirical density and empirical current of this system, of this weakly asymmetric system, which takes the following form. So the probability to observe some empirical current and some empirical density in this time scale equal to some fixed macroscopic profile J rho, which are atypical profile, is given by is exponentially small in the size of the system. Epsilon minus 1 is the size of the system, and the cost to see this some fluctuation in this form is regulated by this large deviation functional, which takes this form here. So you see it is, so you are on some time window 0t, and nu is the strength of the drift, but you have to remember that nu is in fact the real drift, microscopic drift, is nu epsilon. Okay, so it is a small drift. Yes?
What do you mean this J rho on this time? Is this average value on this time?
The average value, here you mean in phase equality?
Yeah.
I mean that for any time t, j epsilon t, rho epsilon t is close to j of t, rho t.
Sometime during the time window or on average?
I mean that here you have some empirical density around some point. Then I say that it is close to some macroscopic profile.
Capital T, is that small time?
No, it is a macroscopic time. It is a macroscopic time. But I look at the system in this time scale. So here I look in the diffusive time scale. So in fact, it is
Small t compared to capital T?
small t. No, t is of order 1. Capital T is of order 1. It's just that if I want to see some evolution of the system, I have to wait for a sufficiently long time. If I just look at some small time of order 1, I didn't see anything.
Just asking about that.
But anyway, it is a standard. It is the way I understand the macroscopic fluctuation theory. It is in this scaling limit. In this scaling limit. So.
Isn't it that it's for every little t in the interval 0 capital T? So you look at this j epsilon rho epsilon to be close to j comma rho. They both depend on little t, and you want this to be true
Yes.
for every little t in the interval 0 capital T.
Yes.
So capital T is
The time horizon.
a restricted time.
Yes, it is a finite microscopic time. So then the rate functional takes the following form. So here I didn't write, but d, sigma, and f depends on the density. Okay, they are not just constant; depends on the rho. And okay, this form is just the standard form of weakly asymmetric system. So you see, in order that this large deviation functional is equal to 0, you need that this term is equal to 0, which is exactly the term which corresponds to the typical behavior. Okay, so the current is just equal to nu f minus d nabla rho. Okay, and this rate functional, which describes the cost to observe some macroscopic profile of the density rho and macroscopic profile of the current J, is given by exponential of minus epsilon minus 2 times this guy. And of course, we have to assume that this constraint is satisfied. Otherwise, we put plus infinity for this rate function, okay? Because the system is conservative, even microscopically. Okay, I will introduce this. I will use this notation along the talk, which is omega, which is the space-time interval in which I look the system at. Okay, in fact, this is the starting point of the macroscopic fluctuation theory, and it has been established for a large class of microscopic system, stochastic microscopic system. Starting, for example, from weakly asymmetric lattice gas, you can prove that the large deviation functional which appears here is exactly you can prove it. You can prove that it is really what you observed. Okay, and this will be my starting point. But I will be interested in this talk in the large deviation functional corresponding to the density. So if you want to compute the cost to observe the macroscopic profile of the density, you have to take the previous large deviation functional, and you have to take the infimum over all the possible currents, J. Okay, and this functional here describes the cost to observe a density profile rho during the time window 0t, 0 capital T. Okay.
Is it a stationary state?
It is not the stationary state. Here, rho is
fluctuation in the stationary state.
Yes. Okay. I mean, here it is a function of x, so it is a probability to you don't have this. Okay. Yes. Okay. Yes. If you don't start with the stationary state, you have to introduce some extra cost to observe the. Yes, you're right. Okay, but this extra term is not very important. Just can be computed in terms of the entropy. Okay. Now I will move to the strongly asymmetric driven system. So here, to derive this large deviation function, what we assume is that the drift is of order the inverse size of the system, the inverse of the system size. Okay, but now we'll look at systems macroscopically, which are described by a drift which is of order 1, which does not depend on the system size. Okay. So we consider a strongly asymmetric diffusive system where the drift term is now of order 1, not of order epsilon. Okay, and we have always epsilon minus 1, which is the inverse of, which is the system size. And now the typical behavior of the system has to be considered in the hyperbolic time scale, so in a shorter time scale to observe something. So here, and the hydrodynamics of the system are described by the conservation law. Okay, it is exactly the same thing that explained Herbert, but in the case where you have only one conserved quantity. Okay. You have to look at the shorter time scale in order to observe some coherent behavior of the empirical density, and it is governed by a scalar conservation law rather than by some parabolic equation. And formally, this equation is very easy to deduce from the microscopic system, just by assuming that you have the propagation of local equilibrium in the hyperbolic time scale. Okay, but in fact, this parabolic scalar conservation law is more complicated than it appears, because if you look now, okay, it is very easy to write this equation, but it is more complicated to understand what it is. What is the solution to this equation? So I have to introduce the concept of weak solutions. It is well known that if you start, you have some scalar conservation laws like the one that I wrote before. In fact, if you wait for some small time, then usually you have some discontinuity which appears. Okay, so you don't have classical solution to the conservation law. You can try to solve it by the characteristics, but at some time the characteristics cross and you cannot define the function, the solution of this scalar conservation law. So you have to find some other way to define what is the solution to this equation. Okay, and of course the natural idea is just to take, since you cannot write the derivative of rho because it doesn't exist, or the gradient of rho because it doesn't exist, what you do is that you multiply. Formally, you do as if it was a smooth. You multiply by any test function, phi, in space and time, and you perform some integration by parts. So if you have a classical solution satisfying this equation here, and you multiply by function phi, and you integrate in space and time, what you will get is exactly this equation, which is written here. So, and you can say, okay, a solution of my scalar conservation law is just a function rho which satisfies this equation. So it is nicer because here you don't have to take the derivative of rho in time or space. So even if rho has some discontinuities, it is not a problem to consider this equation. It is well defined. So the problem with this notion of solution, it is that weak solutions are not unique. So you can say, okay, I call a solution which satisfies the equation, but a weak solution usually is not unique, and so it doesn't describe the typical behavior of the microscopic system, since you expect that there is only one profile which describes the density of your microscopic system. So you have to impose some extra condition in order to restore uniqueness in this set of weak solutions. So at first sight, it seems that weak solutions are not very physical, but we will see that in fact they are a physical meaning. So just for example, start with the Berger equation in dimension 1, okay, and you start with the initial condition 0. So a classical solution is just the solution which is equal to 0 for any time t. But in fact, if you look at this diagram, you can show that for any p here that you choose, every positive p, this kind of solution is a solution of the Berger equation starting from the flat profile equal to 0. Okay, so you don't have uniqueness of the solutions. So what is the real solution which describes the macroscopic system, the macroscopic behavior of the system? So this behavior is in fact described by entropic solution. So what is entropic solution? So entropic solution is defined through entropies, and now it is what I will explain. So it is a concept coming from the PDE's theory. What you do is that you choose any convex function, which will be seen as some entropy. Okay, it is not the entropy of the microscopic system, but it could be. It is called entropy in the PDE's literature. Okay. And then to this entropy, which is just a convex function, you associate some entropy flux, which is given by this field, which satisfies this equation in terms of the drift. And then you say that the weak solution is called entropic if it satisfies this inequality for any convex function eta. And this is what we call entropic solution, and it can be proved that the entropic solutions are unique among the weak solutions. And moreover, it is the solution which is obtained when you look at the system in the large time scale, and which describe the unique entropic solution, describe the macroscopic behavior of your system, of your macroscopic system. Okay. So this has been proved for some several stochastic system. And in this sense, you see this is some this entropic inequality, in fact, is related to the second principle in the sense that, okay, when you write the equation of the conservation law, you write just a part of the just a small part of the behavior of the system, and in particular, you don't take into account the fluctuations, but you know that corresponding to this macroscopic behavior, there is also some entropy which will be which will satisfy a second. So the entropy of the system, the microscopic system, should decrease along the time evolution of your microscopic system, and it is exactly what expresses this entropic inequality. So the entropic solution is the only solution which dissipates entropy in this sense. Okay, if you don't like entropic solution, you can see it in some other way. You can just add some small viscosity to the system, then this equation is well defined. And if you look at the limit as the viscosity comes to 0, then the rho epsilon, the solution of this equation, converges to the entropic solution. And moreover, you can show that the entropic inequality is satisfied for this equation, for this rho epsilon. So it will persist in the limit as epsilon goes to 0, and it will explain why we introduce this concept of entropic inequality. Okay, so the entropic equation, the entropic solution represents the typical behavior of your macroscopic system. Okay, and now we are interested in the cost to produce some atypical profile. So the entropic solution is a typical profile corresponding to this conservation law, and we would like to see what is the cost to produce a fluctuation of the density in this hyperbolic time scale. Okay, so if you remember the functions that I introduced before for the weakly asymmetric system that I denoted by this h nu, gives the cost to produce a given density fluctuation equal to rho for the weakly asymmetric system in the diffusive time scale. Okay, now we are interested in the in the strongly asymmetric system. So, and this call will be denoted by h infinity. It is the cost to produce a fluctuation in the hyperbolic time scale t epsilon minus 1 when the drift is of order 1. So formally what you can do is you use this result, but you take now nu of order epsilon minus 1. So if nu is of order epsilon minus 1, then the drift is of order 1, and you can expect that this large deviation function is related to this one by taking, in fact, nu equal to epsilon minus 1. So you expect that you have this equality which is written here. So if you look, since you are looking in the different time scale, hyperbolic time scale, which is shorter than diffusive time scale, and since essentially nu is equal to epsilon minus 1, you expect that the cost to produce a fluctuation for the strongly asymmetric system is related to the cost to produce a fluctuation for the weakly asymmetric system by this limit. Okay? And now this is this limit that I would like to study, because here I have some expression here, but I don't have the expression for this one. I would like to compute this one. Okay, let me come back to the one-dimensional case. So in fact, the only proof which exists for in one dimension, and even in one dimension, the only proof which exists is for the TACEP, for the totally asymmetric simple exclusion process, and the proof goes starts directly from the microscopic system. And one can, what proved Jensen Bernardin is that starting directly from the microscopic system, from the TACEP, you can obtain the large deviation functional. You have some formula for the large deviation functional of this strongly asymmetric system. But this is very limited. It is only in the one-dimensional case, and it is only for the TACEP, only for this system. Nevertheless, more recently, there are some paper, nice paper, okay, that I think that physicists don't know because it is very difficult to read for, even for mathematicians, it is difficult to read. But in fact, it is very interesting, I think, even for physicists. So in this paper, they propose the generalization of the Jensen-Bernardin functional, but for general microscopic, strongly asymmetric system in which you don't look at the details of the system, you are just looking at the macroscopic behavior, which is described by this d of rho, f of rho, and sigma of rho. And so they argue that you can obtain this large deviation functional of the strongly asymmetric system by taking this limit as the drift goes to infinity. And they are able to predict some generalization of this Jensen-Vardan functional for a larger class of system, okay, which is not restricted to the task. And these two results are very important because they show that, in fact, this functional is finite if U is a weak solution of the scalar conservation law. Otherwise, if you take a profile which is not a weak solution, then it is infinite. So it means that weak solution has a physical meaning. It is the profile that you can obtain in some fluctuations around the typical behavior. You cannot obtain something else. It is only weak solution, and it means that the weak solution has a physical meaning. Okay, this is not just a mathematical distraction. It means something really. Now I will move to the two-dimensional case, and we try to repeat essentially the computations which were performed in this paper of the people that I mentioned before. And so in the two-dimensional case, we proposed some generalization of the Jensen-Vardan formula, and we like to explain briefly how we can. Okay, this is the proof that the function that we obtain is not obtained rigorously. So, but okay, it should be correct, and it is based on very simple principles. So there are essentially three principles. So the fact is that, so the first thing is locally around a space-time discontinuity point, okay, there is a, you know that if you have a weak solution, you have some discontinuities. And around, if you look around the discontinuity, you expect that essentially your solution looks like a moving step function. Okay, and so you can approximate your solution around discontinuity by a moving step function. This is the first principle. Okay, it moves in some direction k with some velocity v, and it is separated between two values u minus and u plus. So this is a local approximation. And now if you look for a moving step function in this form, you can try to compute explicitly this limit, which will give you the cost to produce some step function in the limit. Okay, this is the second principle you compute for a special class of weak solution, which are in the form of moving step function. And now there is a third argument, which is based on some additive principle, which says that the cost to produce a weak solution is simply the sum of the, is obtained by summing all the individual costs of each discontinuity of u. So let me give you some speech about the local structure of weak solution to explain the first principle, the first step. So you imagine that your discontinuity of your weak solution is described by this manifold, this two-dimensional manifold in this space-time space. Okay, this is dimension 3. Here you have a you say that the discontinuity set is a manifold dimension 2. And you introduce this vector, which is a normal vector to this manifold, okay, which has a time component and a space component. And now the discontinuity set splits the space, the time space, in two connected components, omega plus and omega minus, and you call the limit along these two components by u plus and u minus. And in fact, you can show that by using the fact that U is a weak solution, that these two components are related by what is called the ranking Hugonot condition. So let me give you the picture to explain a little bit more. So here you have the manifold of the discontinuity, okay, and you look, so it is time and space, and you look at a constant time. So a constant time, you have this set of discontinuities. You say that around this point here in space-time, what you see is essentially some moving step function along these directions separating u minus and u plus. So you approximate your weak solution in this small disk by this moving step function. And then we have to compute the cost of a moving step function by evaluating the limit of this moving step function. So now we have a moving step function, okay, moving in this direction, with some velocity prescribed by the ranking union condition, and we want to compute this cost. So how do we compute this cost? So we are not able to do it for any weak solution, in fact. So what we do is that first you take an entropic moving step function in the form of in this form with g, which is just a step function taking the value u minus and u plus. Okay, this is a one-dimensional function here. G is a one-dimensional function, and here it is a function of in 2 dimensions in space. And what we do is that you take the space-time reverse of this entropic solution. When you take the space-time reverse of this entropic solution, U becomes a weak solution, not an entropic solution, okay? Because you have the arrow of time which appears by considering the entropic inequality. And the space-time reverse function is a weak solution, which is not entropic. And this is for this kind of space-time reverse function that we are able to compute the cost, okay? What we do is that we know that this entropic solution can be approximated by a traveling wave just by taking some small viscosity of order 1 over nu. Okay? So in order to obtain some approximation of your real weak solution, what you do is that you take this approximation and you reverse time and space, since u is obtained from rho by taking the space and time reversal. And this will permit to compute the cost to produce a weak solution. So it is what after some, so you have to make some computation to solve some variational formula and so on. But what you obtain at the end is that if you look at this limit, you get some expression which, which takes some explicit expression depending only on the value on the left, on the right of the particle, the vector k, which describe the direction of the shock, and and you have 2 parameters which appears here, which is the diffusion matrix and the mobility. And but in fact, there is a mathematical problem to prove this rigorously. This fact is that in fact I was able to compute this cost only for a very particular class of weak solutions. I took an entropic solution, I time reversed this entropic solution, and I obtained a weak solution. And it is only for these weak solutions that I was able to compute the cost, the real cost. And the question is, can we obtain any moving step weak solution by just reversing time and space an entropic moving step function? Okay, this is not so clear. In fact, it is even false even in one dimension. And if you want really to prove the thing, you have to prove some density. You have to prove some density result showing that you can approximate any weak solution by in such a way by reversing time in time and space some entropic moving step function. But there is really a difficult problem here, because we don't know what is a weak solution. We cannot describe really how we can produce a weak solution. Okay. So, okay. Now, if you assume that so you use first that you can approximate your weak solution by a moving step function, it is the first principle. Second principle is that you can compute the cost of a moving step function by taking the time reversal of some entropic moving step function. And then you use additive principle, the additivity principle, which says that you can just you sum all the cost of along the discontinuities. So here it is the integral along the discontinuity. St just at time t, it describes the shock locations at time t, and you sum along these discontinuities the expressions that we obtain for a moving step function. Okay, and we get some expression for the cost to produce a weak solution in the 2D dimensional system, which makes appear this vector nx, which describe the direction of the shock, of the discontinuity. Okay, so let me just compare with the one-dimensional case. In the one-dimensional case, what so in the one-dimensional case, what you obtained with respect to this formula, it just so it is in one dimension. So here the manifold it is not a curve; it is just a point, and this guy which is here. So in this case, you don't have a vector; you have just a scalar. So what appears is that the term which appears in this formula, which is here, was just given by this function, which is just related to the thermodynamic entropy. It is the second by the Einstein relation. It's just the second derivative of the entropy. And we see that in the two-dimensional case, we are just replace this factor by this expression. So you are looking at the shock in some direction, and locally you approximate your diffusion coefficient by this scalar product, and the mobility by this one. Okay, so a posteriori, maybe it seems to be trivial to make this replacement, but at the beginning, you don't. If you didn't have the result, you have several ways to replace this guy. So you could consider, for example, d times sigma minus 1, the matrix d times sigma minus 1. It is not so clear at the beginning how to replace this term if you want to extend the result in the one-dimensional case. And it turns out that it is this one. Okay. So I think I will, okay. So maybe I will skip this part. So in fact, one may also obtain a variational formula for the generalized Jensen-Vardan functional by using some kinetic interpretation of the scalar conservation law, but it is a little bit long, so I will not, I will skip this part. Okay, so we were able to compute the generalization of the Jensen-Vardan functional for two-dimensional strongly asymmetric systems. And so what we would like to do now is, in fact, to study to try to put the system in contact with different baths and to use this result to deduce what should be the large deviation function of the stationary state, the non-equivalent stationary state, when you put your microscopic system in contact with some density baths or something like that in several dimensions. So this has been done in one dimension by Bernardin and Bodino Derrida. And then, okay, maybe if we can do that, we could obtain by doing the variational problem, obtain the quasi-potential, meaning the non-equilibrium free energy of the non-equilibrium stationary state for 2D asymmetric systems. Okay, of course, it would be also interesting to consider the case of multi-component system, but it seems to be very difficult. And okay, maybe now we will able to use these results to deduce some property of the steady state of some active particles, which were initial motivation. But at this time, we didn't find. In fact, Julien asked us some questions, and we looked at the literature, and we were not able to find the precise results that we need. So we turned to this paper of Bertini and Mariani to look at what we can deduce in two dimensions. Okay, thank you. Thank you.
Any questions? Yes.
Okay. for the scalar case, I mean, let's say in 2 or maybe even higher dimension, I mean, do you know that the only singularities which you can have are this kind of shock type singularities, or could the solution be more complicated?
What do
For the scalar case, I mean, the
Yes.
one which you studied in higher dimensions, I mean, let's say
yes,
2
in the scalar
dimensions.
case, yes.
I mean, do you know that the only singularities which a solution can develop are this type of, you know, jump, I mean, shock type of solutions, or could you have more complicated type of
Yes, so
behavior?
in the case where you have only some, for example, convex flux, in this case you have only shocks or anti-shocks. Okay, but in the case where you have some function which is not convex, you have you don't have only shocks and anti-shocks. So in fact, it is a density argument that I mentioned. You have to decompose your shock into several multi-anti-shocks. Sorry, your discontinuity into discontinuity. But rigorous proof is
But
still.
it's always shocks. I mean, nothing more complicated. I mean, you could, you know, if I think function, we could have all kind of discontinuities, right? I mean, but it's always shocks. That's what you're saying, right?
Yeah, but it's not always shocks and anti-shocks. There are also more complicated things.
Other questions? Okay, just a very quick one. So in the derivation, you do it in 2 limits. So you send epsilon to 0 and then nu to infinity. So you do it simultaneously or independently, or is
Yes,
there any reason
independently. So in 2 steps.
you have to do it independently?
Yes, but in fact, in the case of the totally asymmetric exclusion process, it is it is proved because you start directly from the microscopic system, and in the single limit, you obtain the same result.
Okay. And you need some kind of gamma convergence argument for
yes,
the nu to
yes,
infinity. So you
yes.
do like
It has
large
a-
deviations for epsilon to 0, and then you look at the minimizers of the one converge.
Yes, I didn't mention yes, but it is in the gamma convergence settings that we have to understand this limit. Yes.
Okay, thank you very much.